Okay, next variable we want to talk about is water. Water can change. It can change state, it can change its amount, and we're kind of interested in it because, precipitation, clouds, kind of things we want to know a little bit about. So, how does water cycle in and out of the atmosphere? That's kind of an interesting question. We know we have atmospheric rivers. Believe it or not, there are rivers of water vapor in the atmosphere. And you can see a depiction of one coming all the way across the Pacific and hitting the Pacific Northwest here. We had several. A whole stretch of them came into the Pacific coast here during the last few months. And they dumped a lot of rain on California, Oregon, Washington, and that area. And that is just water being transported from the ocean to the land. And guess what? It's going to flow back into the ocean. And so let's just talk about the total amount of water in the atmosphere is relatively small. Almost all of it is confined to the troposphere. And if you dropped all the water that's in the atmosphere, basically you would average about an inch of water over the land. And water continually enters. So how does this work? So I just showed you an atmospheric river. Well, that atmospheric river was getting fed by evaporation from the Pacific Ocean. That eventually formed clouds, hit the mountains in California, Oregon, and the Pacific Northwest, dropped heavy rain and snow. Oh yeah, rivers flooded. Well, guess what? Those rivers eventually flowed back into the Pacific Ocean. So that water, whole process, all that dumping of rain out of the ocean got fed back to the ocean. Yes, some of it wound up going into the land. Some of it could be used for groundwater storage, maybe also to help out the plants that are growing out there that we kind of use. All of that feeds in back and forth. If you looked at around us, Lake Erie gives water off to Ohio or the Great Lakes. Around my house, I get it from the Gulf of Mexico. You do too. Many of the Midwest comes up from the Gulf of Mexico, the moisture. So depending on where the moisture is coming from, maybe how much moisture you're going to get. Which is a bigger body of water, the Gulf of Mexico or the Great Lakes? The Gulf of Mexico is a lot bigger. So if the moisture is traveling from the Gulf of Mexico, there's a lot more of it than if it came off the Great Lakes. So one of the interesting things about water, and it's the only element in the atmosphere that does this, it changes state. So water can evaporate, it can condense. Transpiration is basically comes out of plants, believe it or not, in the late afternoon and evening. If you think about it, in the summertime, the amount of water in the atmosphere actually increases because of plants. All the plant growth sends water into the atmosphere. Sublimation is just getting evaporation, basically, of ice. Deposition is when something vapor becomes a solid right away. So how do we describe all this moisture? We have humidity. That basically describes the amount of water vapor in the air. So summer days are quite humid. There's a lot of moisture in the air. Wintertime can be pretty dry. And here you see a list of how we measure humidity. So let's talk about each one of these a little bit. Vapor pressure. Every gas in the atmosphere has a pressure. We've talked about Dalton's law that says if I measured every atmospheric gas's pressure, added them up, that would be the total pressure that hit you. We just talked about pressure. So up to 4% of the atmosphere's mass in the lowest kilometer can be water vapor, but there's a lot more atmosphere than that, obviously. And it varies a lot. So we want to know how much water vapor is in the air. Another way of measuring that is the mixing ratio. It's the mass of water vapor per mass of the remaining dry air. So you took a parcel of air, subtracted out the water vapor, what was left was dry air, and compared those two. However, you could do specific humidity, which, you take out the mass of water vapor and compare it to all the air that was in that parcel, including the water vapor. So that's the difference between specific humidity and mixing ratio. And absolute humidity is the mass of water vapor per volume of humid air. So saturated air. Well, we just talked about water vapor in the air. Well, it's saturated when the air can't hold any more water vapor, and when it's literally going to force the air to condense that water vapor out. So when you see clouds, that's saturated air. When you see fog, when you have dew on the ground, that air has become saturated, or frost. So air reaches its maximum humidity and then will gradually change over, condense into clouds, little balls of water in the sky, droplets. So there are some terms, all of them with saturation. So we just talked about vapor pressure, saturation vapor pressure, saturation specific humidity. Changes in air temperature disturb this equilibrium of water. Heating the water increases kinetic energy of water molecules so they can more easily escape from the water surface. So that is why a higher temperature of air can hold more water. Lower temperature air holds less water. And here you actually see tables. And guess what? Critical thinking this week, you're going to need to use one of these. So if you had this table here, we knew the temperature, we would know what the saturation vapor pressure is. Notice when it starts getting warm, it really goes up pretty quickly. So it can hold a lot more water when it's fairly warm than when it's cold. And oh yeah, ice. Ice has a different vapor pressure. Why is that? Well, ice is solid, so you don't have as much motion of it. So therefore, the vapor pressure over ice is actually going to be less than over water. That will be important later on. So now relative humidity is basically vapor pressure per saturation vapor pressure times 100. So if I have a vapor pressure of 20 and I know the saturation is 25, well then you just divide them, multiply it by 100, and that is your relative humidity. So basically relative humidity is measuring how close we are to saturation, the air. Doesn't tell you how much amount of water is in the air. You can have 100% relative humidity and it could be 0 degrees outside. And that amount of water is going to be very different than the amount of water that's in the air if it's 100 degrees outside and I have 100% relative humidity. And here you can see how the relative humidity changes. So the colder the air gets, the less moisture it can hold. Relative humidity is going to go up at night. That's why we have fog in the morning. Now, during the daytime, the relative humidity actually is going to drop as the temperature rises because the air can hold more. Interestingly, sometime in the late afternoon, a lot of times, evapotranspiration spikes the relative humidity just a little bit, not a lot. So that transpiration coming out of the plants can actually increase the moisture in the air enough to actually raise the relative humidity. Dew point's just a measure of if you cooled the air at no change in pressure, when that air would reach saturation. That is why it's plotted on a weather map. That's why it's important to us. You look at the temperature and you look at the dew point. How close are they together? If they're exactly the same, you know it's 100% relative humidity. If they're very, very different, you know it's very dry air. And you can see how the dew point changes. January, it's fairly cool. In the summertime, look at how much warmer it is. Interesting fact. I didn't know this, but I happened to be working with some researchers at Oklahoma University who did research in humidity, moisture, dew point in their wheat belt. When their wheat is growing, evapotranspiration keeps the dew points in the 60s and even close to 70 many days. Once they cut that wheat, say in the middle of summer, that same dew point, same kind of air mass, will have dew points in the 50s and low 60s. That evaporation from those plants made that kind of a difference. So if you look at the Corn Belt in Iowa, sometimes in the summertime, you see very high relative moisture. Dew points go up. Once that corn's harvested, the dew points are going to come back down. So as air becomes saturated, it produces the cloud, the droplets. How does the humidity increase? Well, if air is cooled, we know it's cooled as it's rising, and the same amount of moisture is in that air, the colder the air parcel gets, the lower the saturation vapor pressure gets till they equal the vapor pressure of the air, and you wind up with ice crystals or water droplets. All right, we're going to move on from this. So now that we've got the amount of moisture in the air, we're going to talk a little bit about stability. Any of you ever seen a bird just kind of circling? It kind of just seems to stay at the same altitude, never flapping its wings. Or have you ever been in a glider that goes up, up, up in these thermals? Well, that's all based on stability. Air will rise if it is warmer than the surrounding air. And you're going to hear me talk about air parcels. Air parcels are any size you want to call them. It's just a parcel of air. I don't care if you call it 2 inches across by 2 inches across or a mile across by a mile across. It's a parcel of air. That parcel of air has so much moisture in it, it has a temperature. Next to that parcel of air may be a very different temperature or slightly different. I lift that parcel of air up. As it's rising, the temperature is dropping. We know dry air drops at 9.8 degrees Celsius per 1,000 meters. So as that air parcel is rising, it's dropping that way. The air surrounding it may not drop at that same rate. Almost all air does not drop at have a temperature drop at 9.8 meters, 8 degrees per 1,000 meters. Most of it, you're going to find a lapse rate anywhere from about 7 to close to 8.5 degrees per 1,000 meters. So I'm taking this air parcel, if I'm rising it and I'm cooling it like that, I'm going to be a lot colder than the surrounding air. That air parcel, because it's colder, it has more molecules in it, they're denser. You know that from earlier learning. That air parcel is going to want to sink. So if it's colder than its surrounding, it is going to tend to sink. If it's warmer than the surrounding, well, how would that happen? Well, take moisture, we condense it, it heats the air, and we know, or you're going to learn, that the moist adiabatic lapse rate, or the lapse rate of temperature, when it's saturated, is only 6 degrees. Well, now that surrounding air that used to say be at 8 degrees dropping, all of a sudden, when we moved up, is now next to it is only dropped 6 degrees. That's 2 degree difference in 1,000 meters. That 2 degrees is a lot, and that air parcel is going to want to accelerate upwards till it can reach the same temperature as its surrounding. That's what makes the difference between unstable and stable air. The more unstable the air is, the faster it's going to accelerate upward. The more stable the air is, the faster it's going to want to fall down towards the earth. So, we just talked about all of this stuff. What causes air to rise? Well, Earth heats the air locally around it. It gets a little bit warmer than its surrounding. It starts to lift. You see that in cumulus clouds. Eventually, it cools. Condensation takes place, but maybe there's not a lot of moisture there, so just a little bit of a cloud forms. Now it begins to dry out. That air starts cooling a little faster than the surrounding air where the cloud was. It's going to sink back down to Earth because it's now colder. Fronts. Warm fronts can lift air up. Cold fronts can lift air up. Cold fronts tend to be a little steeper because they're colder. They're dry, more condensed air. Put it tight. Mountains. In West Virginia, you have mountain ranges that air hits, and they're going to have to go up. And if the air is dry, well, it's never going to form a cloud, but it's going to keep rising up. until it comes down the other side when it's going to really pop down there very fast. So let's just look at today, for example, what's going on out here. Here is the dew points. We talked about dew points a lot already. Well, let's take a look at dew points here today. 73, 73 in the Gulf of Mexico. That's a pretty warm dew point. Because notice back here, 35, 50. Well, drier air. 45, 36, 9 degrees apart. So you can see moisture coming up on this side of the cold front, colder, drier air on the other side of the cold front. So you can actually see the change in dew points with that front as well. And there are things like dew point advection. We talk about called temperature advection, but you can sure advect moisture just as easily. And finally, I just wanted to look at this loop. I paused it here. We got lots of rain going on in the Gulf of Mexico, in the Gulf Coast states. Notice where the moisture is coming from. This is the band of moisture. It is literally coming off the Pacific, up across the Gulf of Mexico into that area. Guess what? There's a ton of moisture in that part of the world. So yes, that's why it's raining fairly hard in some of that area. So knowing where the moisture comes from sometimes is very key to just how much of that rain, how much precip you're going to get. So I hope you got a little bit out of this, and let me know if you have any questions.